Welcome to today's Explainer. I am absolutely thrilled you're joining us because today we're untangling one of the most fascinating and honestly kind of crazy paradoxes in modern tech. Picture this for a second. We live in a world completely surrounded by tiny battery-powered IoT devices. We're talking sensors, smart cameras, microcontrollers, things with barely a few kilobytes of RAM. And yet somehow they're expected to interact with massive, highly complex deep learning applications. I mean, how is that even physically possible, right? Well, we're about to find out, and the architecture behind it is absolutely brilliant.
Okay, let's dive into this. Here is our highly organized roadmap for today. First, we'll look at the IoT solution. Then, we'll compare binary versus partial offloading. Third, we'll break down the math. After that, we'll explore fog resource allocation. And finally, we'll wrap it all up with the master flow.
All right, kicking things off with Section 1, the IoT offloading solution.
I want you to paint a really vivid picture in your mind. Think of a tiny, overworked edge device, maybe a small environmental sensor running on a basic coin cell battery. It is literally sweating under a massive computational load. This brings up a really critical question. If these edge devices are so fundamentally weak and constrained, how on earth do they run complex modern applications? We're talking about incredibly intensive stuff here, like real-time video analytics, augmented reality, or even autonomous navigation for drones. If they actually tried to process this locally, they'll either crash instantly or drain their battery in a matter of minutes. So what exactly is the secret?
Well, the answer is task offloading. Instead of trying to do all that heavy lifting themselves, these tiny, constrained devices play an incredibly intelligent, high-speed game of pass the parcel. Basically, they take these massive computational tasks and push them over the network to nearby, significantly more powerful fog or edge nodes. The fog node does all the hard work and then just casually passes the finished result right back. It's a lifesaver, really. It's the exact mechanism that saves the tiny device's battery and keeps our entire smart network alive.
That brings us to Section 2, binary versus partial offloading. Because to truly grasp this architecture, we have to understand how these tasks are actually handed off.
Now, what's really interesting about this slide is how we can sharply contrast these two primary models side by side. Over on the left, you've got binary offloading. This is a very strict, all-or-nothing approach. And on the right, we have partial offloading, which is much more of a divide-and-conquer strategy, usually mapping things out using what developers call directed acyclic graphs, or DAGs.
Let's look at binary offloading first. Imagine you've got a smart door lock. Its one job is to authenticate a user's face to unlock the door, right? But the facial recognition algorithm is this massive single chunk of code. You absolutely cannot split that task into smaller pieces. So the smart lock is forced to make a binary choice. It can either try to compute the whole algorithm locally, which, let's be honest, probably can't, or it sends the entire raw image over the network to the fog node and just waits for a simple, lightweight yes or no to come back. All or nothing.
On the flip side, partial offloading is built for those highly complex applications that you can actually modularize. Take an augmented reality headset, for example. The app has multiple subtasks. Using that directed acyclic graph we mentioned, developers map out the dependencies. So the headset might decide, hey, I need to compute the eye tracking locally because that requires zero latency, otherwise the user gets motion sickness. But at the exact same time, it offloads the super heavy 3D graphics rendering to the fog node sitting on your Wi-Fi router. The device and the fog node are working together simultaneously. Divide and conquer in action.
Let's shift gears a bit. Section 3, the math of decision-making. Because you might be wondering, if offloading is so amazing, why don't devices just do it for everything? Well, they can't just offload blindly, because wireless transmission itself is a massive drain on the battery.
Turns out, the system uses a very strict mathematical decision engine to evaluate its energy limits. Let's walk through the formula. An IoT device is only going to offload a task if the energy it takes to transmit the data, plus the energy it takes to receive the result, is strictly less than the energy it would cost to just compute it locally. Make sense? Basically, if transmitting the data over Wi-Fi actually burns more battery than just doing the math on the device itself, it cancels the offload request. The device is selfish, in a good way. It will only offload if the energy math works out completely in its favor.
And this brilliantly illustrates our second major constraint, delay, because it's not always just about energy. Think about a self-driving car that suddenly needs to detect a pedestrian stepping out into the road. In that split second, battery life absolutely does not matter. Speed entirely overrides any energy concerns. The transmission time, plus the processing time at the edge, plus the time to get the answer back, absolutely must be less than or equal to the deadline.
If the network is congested and this latency formula fails, the car is forced to process locally, even if it drains the battery. Because missing that deadline, that means a catastrophic failure.
Okay, let's zoom out from the tiny edge device and look at the big picture in Section 4, Fog Node Resource Allocation. From up here, the fog node is dealing with a totally chaotic, incoming conveyor belt of offloaded tasks from hundreds of different devices.
Now, the fog node is powerful for sure, but its resources aren't infinite. It only has so many CPU cores and RAM to manage all these incoming connections. To handle this, it uses a resource broker packed with scheduling algorithms. For standard everyday management, it might just use basic algorithms, things like round robin or shortest job first. These are low complexity, but they get the basic job done.
But here's the catch. Wireless network environments are incredibly dynamic. Devices are moving around, signal strengths are constantly fluctuating. To bring order to this chaos, modern fog controllers rely on advanced heuristic optimization algorithms. We're talking about highly sophisticated mathematical models here, like particle swarm optimization and game theory. These are absolutely vital because they dynamically allocate CPU cycles on the fly. They literally prevent individual servers in the fog node from overheating, while at the exact same time minimizing the overall latency for every single connected device. It is a massive juggling act.
So we've covered the hardware constraints, the models, the math, and the algorithms. Now it's time to put it all together in Section 5, the master execution flow.
Let's move to and see how this builds into one definitive chronological sequence. We've got a 6-phase master lifecycle flowchart here. Step 1, task generation. The tiny IoT device encounters a computationally heavy task. Step 2, context profiling. The device quickly checks its own battery level and the current network bandwidth. Step 3, decision-making. The local agent runs those energy and latency math formulas we just talked about. Step 4, transmission. If the math actually checks out and offloading is viable, the raw data is pushed over the wireless channel. Step 5, resource allocation. The fog node receives it, drops it in a queue, and uses those advanced heuristic scheduling algorithms to assign it to the best available CPU cores. And finally, Step 6, execution and return. The fog node crunches the heavy data and fires the lightweight, finished output right back to our tiny edge device.
So, what does this all mean? Mastering this entire system ultimately comes down to one really provocative trade-off. How do we perfectly negotiate saving the tiny, delicate IoT device's battery on one end against efficiently balancing the massive computational load of the fog node on the other? It's this continuous, high-speed negotiation happening literally millions of times a second all around us. And understanding this perfectly sets us up for our next explainer, where we're going to dive into exactly where these tasks execute inside the fog node, comparing heavy virtual machines against lightweight Docker containers. I really hope this structured look at task offloading empowered you with a crystal clear understanding of the architecture. Thanks so much for joining me today, and keep that curiosity fired up